In this lecture we talk about degree of an isogeny. So say we are given an isogeny in a standard form like this. So p over q, this is a rational function in x, this s over t is a rational function in x, and you just have a y here. So this is just the standard form of isogeny. Then the degree of this isogeny is maximum of the degree of the numerator and denominator. So the maximum of the degree of p or q. So notice that we are only worried about this first term for computing the degree of the isogeny. And this isogeny is called separable if the derivative of again this first coordinate is non-zero. So if the derivative of this first coordinate is non-zero, then we call the isogeny as separable. So let us see some quick examples. So first is a doubling the point. So we have seen this isogeny. This isogeny has this form. So again we are keeping the second coordinate as such because it is the first coordinate which will tell us the degree as well as the separability. So this is the rational form for doubling the point, and this is of degree 4. As you can see, it is degree 3 in the denominator and 4 in the numerator. So the maximum of 4 and 3 is 4. So degree is 4, and this is separable. You can take its derivative and you will see it is not 0. Now sending a point to its negative. So that is this xy goes to x minus y. So this is again a map of degree 1. As you can see, this degree of x is 1 here, and it is separable. You can take the derivative of x, it is just 1, which is non-zero. So now another example is Frobenius endomorphism. So we assume that the characteristic of the underlying field of our elliptic curve is not 2, and we are going to work in this finite field here. So we have this map xy goes to xq yq, and again you can see the degree of isogeny here is q. So you get degree of isogeny is q, which is degree of xq. But if you take the derivative of this first term, you get q xq minus 1. Now notice that this coefficient is q. So in a finite field this is 0. So this becomes 0. So therefore this Frobenius endomorphism, this is inseparable. So we have seen example of 3 isogenies. First 2 were separable and the third one is inseparable. So now we give an easy characterization of inseparability. So separable means that the derivative is not 0, and inseparable means the derivative is 0 of this first coordinate. So it has two implications. Number one is both p prime and q prime would be 0, and number two is that you can write this p of x as fxm and q of x as gxm, and where this m is nothing but characteristic of the underlying field k, where f and g are both polynomials here. So notice that we are working with an isogeny. So this k refers to the field over which elliptic curve is defined. So our elliptic curve is defined over k, and then our isogeny is defined over this E, which takes this elliptic curve to another elliptic curve. So before we prove the lemma, let us see an impact on a corollary. So if the characteristic of k is 0, then every isogeny is separable. So this you can see directly from here. So if characteristic of k is 0, then you plug in 0 here, you plug in 0 here, you get p and q as constants. And so if characteristic of k is 0, then this in isogeny, this first term has to be a constant, and therefore it will no longer be an isogeny. So therefore it has to be the case that we have a separable isogeny, because if we have inseparable, you plug in here, you have to have constants and constant here, which will no longer make it an isogeny. So this is easy corollary. So let us now prove this lemma. So we take the derivative here. So we are focusing on 1. So you take the derivative, this is what the derivative is, and this entire thing is 0 if and only if the numerator is 0, and we are writing the numerator like this. So first direction is really easy on number 1 from here to here. So you plug in p prime 0 and q prime 0, you obviously we get everything as 0. So this direction is easy, there's nothing to prove. In the opposite direction, in this direction, you know that p over q prime is 0 will lead to this statement right here. Now q and p are relatively prime, so this q and this p are relatively prime, so it must be the case that q prime and q have common roots. So this q prime and q have common roots. So if they have exactly the same number of roots, then it has to be the case that the q prime is 0. Now that is because degree of q prime is less than degree of q because you're taking a derivative. So degree of q prime becomes less than degree of q, and that makes it impossible to have exactly the same number of roots with multiplicities. You count the multiplicities as well. So we have been able to show that q prime is 0. Now similar story you can tell with p prime, and p prime would be 0. So this one is done. So for number 2, first we write down the polynomial like this. You know the polynomial you can write as summa ai xi. Then you take its derivative. P prime you can write I ai xi minus 1. So first we go in this direction. So we have just taken the polynomial and its derivative, and you say this derivative is 0. So this is 0 in our field with characteristic m. So it must be the case that m should divide I for all I. So we rewrite this polynomial as something like this: alpha j x to the power of m j. So instead of alpha you can just write it as aj, and you write it as x to the power of mj because now instead of I, this m divides I, so you have to write it as a factor. So say our mj is now I, so you are setting I is equal to mj. So that's it, and then you can write it as f of x to the m. To be more precise, instead of alpha j you can rewrite it as a, instead of I you can put in mj, but that doesn't make any difference because our polynomial is now in terms of x to the m. So we have been able to go in this direction, and you can obviously again go back in the backward direction. So if the polynomial is given as px is f x to the m, then you can take its derivative and you will have this m sitting out here. So once you have m sitting out here and you know the characteristic of our underlying field is m, this is equivalent to 0 in our finite field with characteristic m. So in characteristic of k equals to m, this is 0. So we have been able to prove number 2, and the same story you can tell for q. So the next proposition we want to prove is this. So we can write some inseparable isogeny. So you say you're given an inseparable isogeny like this, you can write it as something like this. First factor is a rational function, but is x to the power of m. Second factor is also a rational function, x to the m, but you have this y to the m here instead of y, and both of them are rational functions over field k. So r I k of x. So basically rational functions means polynomial over polynomial, and again as before, characteristic of the underlying field is m. So let us prove this proposition now. So we are working on elliptic curve E1 and E2, and isogeny is taking this elliptic curve to say elliptic curve E2. So this is our isogeny. So this is the isogeny. So what we are doing is we are going to plug in for y square and x cube and x these coordinates. So for x you plug in p over q, and for y you plug in s over t. So you get this y square, instead of this y you have s by ty, that's what we have plugged in, and for x we have plugged in p over q. Now you start taking the derivatives. This is just a constant, will be 0, and we are talking about inseparable isogeny. So the derivative, this p over q prime, is 0. So what we are going to get is s square over t square y square prime would be 0, and now we can use this result. You have, instead of p you have now s square y square, so that is some g to the x to the m, and t square is some h x to the m. So now notice that this g x to the m has roots with multiplicity m in the closure of k, but we are talking, this y square is essentially this elliptic curve right here. So we know that this elliptic curve is non-singular. So since this is a elliptic curve is non-singular, this does not have repeated roots. So this y square does not have any repeated roots. So therefore we have to rewrite this equation again. You can again rewrite as sy is g1xm times ym, and now you have a rational function. So that's it. You have g1xm ym, and in the denominator we are saying t square is hxm, but you can get rid of this square here by by actually taking this 2 out in the derivative. So you can rewrite this as twice s over ty derivative, and then there will be no square to worry about. So then again you can write sy as something and again come back to the same thing. So anyway, this is nothing to worry about. So you do get a rational function like this. You get sy as some rational function, and then you can write t as some rational function, and you put it here. You obviously cannot take a square root of a rational function because that is no longer a rational function. So we have to think about getting rid of the square, and I think my idea is simple. Just take 2 out, and that will get rid of the squares because you're taking a derivative. So we have been able to show that the second form, this rational function here, this came from s by t y, this became a function in m, this became ym, and this obviously comes from p over q. We have seen that we have inseparable, so p by q prime is 0, and therefore this p of x is a function of xm, denominator is a function of gxm, so this p over q becomes fxm over gxm, which is a rational function. So a corollary of this proposition is that every isogeny over field K, if characteristic of K is given to you as M, this can be written in this form: phi separable, Frobenius n times n is greater or equal to 0. And this Frobenius map basically takes this xyz to xm, ym, zm. Now this is easy to see. If your isogeny is separable, you just take n as 0. Now if it is inseparable, then you know it is of this form. Now to get to this form, you first have this isogeny phi 1, which is our r1 of x, r2 of x times say y, because it has to be some standard form like this. Then you apply Frobenius to it, and you land in this isogeny, our isogeny, which we know this is the isogeny because we are working in the inseparable case. Now the only question arises is, what if this phi 1 to start with was inseparable? Then you just use this procedure recursively. You find another rational functions like this and you apply Frobenius again. So you keep doing this, and obviously this process has to stop at some point in time because your degree is finite, and this degree of phi would be just m to the n, and then the degree of our initial separable thing, because every time you apply a Frobenius map, you are increasing the degree by m. So if you apply a Frobenius map n times, you have m to the n, and this initial degree is just degree of this.